Hi, I'm Temitope Adeniji and you're welcome to Avogadro Chem Clinic, where chemistry becomes crystal clear. In this video, I'm going to analyze the step-by-step to solving gas law problem. In my previous video, I explained the four main variables to be considered when talking about the gas laws. The variables are, we have the pressure, volume, number of mole of gas, as well as temperature. So the pressure can be measured in several units such as atmosphere, ATM, Pascal, Newton per meter square, torr, bar, as well as millimeter mercury, mmHg. But the SI unit of pressure is Newton per meter square. That is the SI unit of pressure. At standard pressure, we can have the respective values given to pressure as standard pressure, we have the respective value for pressure as 1 atm, which is equivalent to 760 millimeter mercury, and equivalent to approximately 1.0131 times 10 raised to power 5 Newton per meter square. We also have the older unit of pressure as bar, 1 bar, which is equivalent to 760 torr, also equivalent to 1.0131 times 10 raised to power 5 Pascal. So pressure can easily be converted by taking these values as reference standard. The next variable is volume. Volume can be measured in meter cube, liter, dm cube, centimeter cube, etc. The SI unit of volume is meter cube. Volume conversion can be carried out using this trench. I have meter cube to dm cube to centimeter cube. When I'm going in this direction, all I need to do to the units is to multiply by 1000. When I'm moving in the reverse direction towards this direction, that is from centimeter cube to dm cube to meter cube, all I need to do is to divide by 1000. So in an instance whereby we are to convert centimeter cube to meter cube, that implies that we are going to have 1000 in two places, which is 10 raised to power 6. And it implies that I'm going to divide by 10 raised to power 6 in order to achieve what? Meter cube from cm cube. The next variable that we need to consider is the temperature. Temperature is the measure of the degree of hotness or coldness of an environment or system. It is measured in Kelvin or degrees Celsius. In order to convert temperature from degrees Celsius to Kelvin, 273 is added to the value in degrees Celsius to arrive at Kelvin. In the other way around, if we are to get the value in degrees Celsius, 273 is subtracted from the temperature in Kelvin to achieve the value in degrees Celsius. Now we can consider the fourth variable, which is amount of gas. The amount of gas is denoted as N, and it can be expressed as the ratio between the reacting mass and the molar mass of the gas. We have the reacting mass over molar mass of the gas. Also, the amount of gas can be expressed as the ratio between the number of molecule to the Avogadro's constant. So the ratio between the number of molecule and the Avogadro's constant is the same as the amount of gas. Also, we have the reacting mass over molar mass is the amount of gas that we need to find. The amount of gas is measured in mole. It is measured in mole, which we can also rewrite as, we can as well deduce the number of molecule, number of particle, and number of atom by multiplying the Avogadro's constant with the number of molecule. 6.023 times 10 raised to power 23. When the number of mole is multiplied by Avogadro's constant, we can arrive at the number of molecule, number of particle, and number of atom. Therefore, invariably, it implies that the product of the amount of substance of the gas and the Avogadro's number gives the number of molecule, number of particle, and number of atom. From the question, we can deduce that at the start of the experiment, we can observe that the volume of the gas V1 is V0, while the pressure P1 is P0 from the question. So the piston was pushed downward. So the volume decreases by factor of 5. Therefore, V2 is 1 over 5 V0. That's 1/5 of its volume. That's volume decrease. Then P2 will be what? Recall that from the Boyle's law, we say as volume increases, pressure decreases. Why? When volume decreases, pressure increases. So we are expecting to have an increase in pressure. So from the mathematical expression for Boyle's law, we have P1 V1 equals P2 V2. We are to find the P2. Therefore, we make P2 the subject of the equation. We have P1 V1 over V2. P1 is P0. V1 is V0. While the V2 is V0 over 5. So when we find the reciprocal of the expression, we have P2 equals P0 V0 times 5 over V0. This eliminates this. We are left with P2 equals 5 P0. So when pressure is increased by factor of 5, volume is decreased by factor of 5. So we have a decrease in volume when pressure increases by factor of 5. From this piston, we can see that the volume is greater here, while we have a decrease in volume here. While pressure decreases, pressure drops at those points. And at this point, because the molecule of the gas are colliding with the wall of the container vigorously, therefore pressure tends to increase. On our CYK, we are going to be considering another question on gas law problem. We have the question, a balloon can hold 1 dm cube of air before bursting. If the balloon contains 975 cm cube of air at 5 degrees Celsius, will it burst when it is taken to an oven that is set at 25 degrees Celsius, assuming that the pressure of the gas in the balloon remains constant? I would like you to pause the video and try to attempt the question now. Now let's confirm if your answer is correct for this question. It can be observed that towards the end of the question we have assuming that the pressure of the gas in the balloon remains constant. So at constant pressure is in accordance with which law? We have the Charles law. Okay? From this thing, we can deduce that the temperature is low, which is 5 degrees Celsius. So at temperature T1, we have 5 degrees Celsius. Okay? When we convert it, we have 278 Kelvin. And at volume V1, we are expected to use this volume because that is the volume of air in the balloon. This is the standard for confirmation if the balloon will burst. So we have 975 cm cube. So here is the balloon. We have originally the volume of air in the balloon is 975 cm cube. At what temperature? At 5 degrees Celsius, at a very low temperature. But in an instance whereby the balloon is taken into an oven set at 25 degrees Celsius temperature, you will discover that the volume tends to increase. So if we have an increase in volume, will it exceed the 1 dm cube, which is the standard at which when it exceeds that the volume, the balloon tends to burst? Now the question is, will the balloon burst under this condition when it is taken into an oven? We all know that in accordance with Charles' law, as temperature increases, volume increases. So will the volume exceed the 1 dm cube? That's what we've been asked to find. So let us check the volume of the air in the balloon when it is taken into an oven. So the temperature C2 is given as 25 degrees Celsius. So when we add 273 to it, it becomes 298 Kelvin. We have to find volume V2, the volume of air in the balloon when it was taken into an oven. The mathematical expression for Charles' law is V1 over T1 equals V2 over T2. Okay? Here we have to find V2. So we make V2 the subject of the equation. It becomes V1 C2 over C1. V1 is 975 times our T2, which is 298 Kelvin, and the T1 is 278 Kelvin. When you press your calculator, what do you have? That's right, we have 1045 cm cube. So here is the new volume of air in the balloon when it was taken into the oven. The 1045 cm cube is equivalent to what dm cube? Recall that if we are to convert cm cube to dm cube, we are expected to divide by 1000. So to dm cube, cm cube to dm cube, we have to divide by 1000. So we have 1045 divided by 1000. So this will give what? That's right. We have 1.045 dm cube. So the maximum volume of air that the balloon can hold is 1 dm cube. And this 1.045 dm cube exceeds the maximum holding capacity of the balloon. Therefore, what will happen? Yes, the balloon will burst, okay, when it is taken into an oven set at 25 degrees Celsius. Make sense? Still on gas law problem, we have another question. A container is designed to hold 20 cm³ volume of air at a pressure of 2.0 atm atmosphere and room temperature of 25 degrees Celsius. Would it be safe to throw the container into a fire where temperature of 500 degrees Celsius would be reached? I would like you to go through the question while you pause the video and let me have your answer. You're welcome back. Let's confirm if your final answer is correct. We can look closely at these two charts right here. We're told that a container is designed to hold 20 cm³ volume of air. That implies that the volume of air is not changing in the container, irrespective of the changes that we have in temperature and pressure. So the volume is kept constant. So if volume is kept constant, it is in accordance with which gas law? That's right, Gay-Lussac's law. We have Gay-Lussac's law. Okay? So we have the pressure changing. Pressure P1, at this point the pressure is low as a result of the temperature drop that we have here. Okay, so the Gay-Lussac's law states that the pressure is directly proportional to temperature. So when temperature drops, pressure drops in accordance with Gay-Lussac's law. We have P1 equals 2 atmosphere, C2 equals 25 degrees Celsius. We have 273 to this. We have 298 Kelvin. After the change, we have an increase in temperature, which will result to an increase in pressure. But the pressure is not given in the question. So we have P2 unknown. T2 is given as 500 degrees Celsius. So when we add 273 to it, we have 773 Kelvin. Okay? The mathematical expression for the Gay-Lussac's law is P1 over T1 equals P2 over T2. Here we are to find the P2. We make P2 the subject of the equation. We have P1 C2 over C1. When we rearrange the equation, we have this. P1 is given as 2. Then the T2 is 773 divided by 298. So when you press the calculator, we have 1546 over 298, and the final answer is 5.18 atm. So this implies that as pressure increases, temperature also increases. So in your gas law, you need to know the relationship between the variables so as to know what you are likely to get for the final answer. So here pressure increases. Let's go back to the question. Would it be safe to throw the container into a fire where temperature of 500 degrees Celsius would be reached? We have an increase in pressure, so the safe strength of the container has been exceeded. So it will not be safe to throw the container into a fire that is burning at this temperature, 500 degrees Celsius, because the molecules of gas in the container will continue to collide vigorously with the wall. Okay, and it is not safe for the container. Why? At low temperature, the collision rate of those gas molecule is low. At high temperature, it increases. Remember, the volume is kept constant. So that shows that at this condition, when the temperature is increased, the gas molecule has been compressed in that state. So they tend to find their way out. It can result into explosion. Make sense? Now let's consider the CYK for this gas law problem. I'll be expecting your response in the comment section. So you give an answer in the comment section. So I'll be there to reply you accordingly. The first question, CYK1, we have a balloon can hold 1.1 dm cube of air before bursting. If the balloon contains 975 cm cube of air at 5 degrees Celsius, will it burst when it is taken into an oven maintained at 60 degrees Celsius, assuming that the pressure of the gas in the balloon remains constant? So I want to believe you know the gas law that is in relation to this particular question. So that's CYK1. The CYK2, you are expected to consider the question and drop your answer in the comment section as well. An oxygen gas occupies a volume of 4/9 V cm cube at a pressure of 3/4 P millimeter mercury. Calculate the volume of the gas if the pressure is reduced by 1/3, that's 1/3, of the original value, assuming temperature is kept constant. Here, temperature is kept constant in accordance with which gas law? I believe you know that. Then here, the pressure is kept constant in accordance with which gas law? I want to believe it is well understood. So I'll be expecting your answers in the comment section. For more videos, kindly click the subscribe button and share with your friends right now. You can also like and follow my Facebook page. Thanks for watching.